Okay, so I'm going to continue from last time where we talked about Newton's laws. Now I'm going to talk about where we stopped last time, about how do we measure mass and how do we know if something is heavier. Like, how do I know that this is heavier than this? And also, before I discuss that, I'm going to talk about how do we measure time, like how do you make a clock. Okay, so from last time I told you in Newton's laws, the way that you picture the world is that it just extends to infinity in three different directions, okay? Like this way, that way, and that way, okay? So you have like three different directions, and if you want to get from any point, if you want to get from a reference point to any other point, you just need to give me three numbers, like the numbers that I have to move in that direction, that direction, that direction, okay? So that's x and y and z. But more than that, these points are moving in time, right? So you have some sort of clock. And Newton thought that there's like an absolute time. So there's like a universal clock that is ticking. Okay? So this is a problematic assumption that we're gonna talk about in a little bit. So it's a tricky to think about. But let's imagine you have this clock that's ticking and giving you time, and this point is moving with respect to time. So when we start here, the point is over here, right? So here, the point is here. But then you get to here, but now the point has moved over there, okay? And by knowing x, y, and z as a function of time, so you know x of t, this is a function of time. So this direction is changing with time, this is a function of time, and z is a function of time. You can see how these things change in time. The rate of change of this with time, like how much did this number change after 1 second, how much did that number change after 1 second, how much did the third number change after 1 second. If you do that, you get velocity. Once you get velocity as a function of time, you can do the same thing. How much did velocity change at 1 second? And that gives you acceleration, the change in velocity over time. Okay, but here's the philosophic assumption that there is this universal clock. But let's say, like, how do you know that this clock is ticking at a constant rate? You can't know that. There's nothing else that you can compare it to. All you can do is compare it to a different clock and say, okay, here's another clock. It looks the same. And every time this signal is here, that one is there. So they're ticking together. But you can't know that the time it took for this tick is the same as the time it took for that tick. That's basically an assumption. It's you have to basically hypothesize that and say, like, here's a thing, this is a clock, and it runs at a constant rate. And then you measure everything else in the world with respect to that. And if your laws make sense and the predictions that you follow, when you follow those rules, like Newton's laws given using this clock, if you get consistent predictions, if you predict what's going to happen in the atmosphere correctly, then you're good to go. That's all you can do. You can't prove, for example, what if, like, at the ultimate level, there's this theory that we don't understand, hypothetically, that every second or every millisecond the entire universe freezes. All your thoughts, everything freezes. This just stops there. And it stops there like for an hour. But nobody can feel that because everything just stopped. And then it continues to move. What if that happens every tick? We can't really verify whether that happened or not, because everything we can measure has no signal of that. Okay? So it's a tricky issue here to say there is a clock and it's ticking at a constant rate. That has to be, there's hidden assumptions in there. You're hypothesizing that, you can't really prove it. But in Newton's laws, remember we said F equals ma, and that's what we're going to talk about today. There is an assumption here. If you give me a particle, there's nothing else, nothing is interacting with it, so F is equal to 0. Then this is moving at a constant rate. If it's moving at a constant rate, then the ticks of this particle also gives me a clock, because it's moving at a fixed rate. So if this takes 1 second, then this will take 1 second, so this will take 1 second. So you can, again, hypothesizing that this particle has no forces acting on it. How do you know if there's no forces acting on it? You can't really be 100% sure because this is your clock. Maybe it's speeding up, but you can't tell that because this is your reference point. I hope this is making sense. If it's not, you can ask me more questions. To continue, you can imagine building a clock like that where you make something like this particle, where you have a particle on ice and there's no friction, and then you let it go at some speed, and because there's no friction, there will be no force acting on it. Here's where the assumption is coming in. You have to assume that there's no force acting on it. But once you assume that, you use this as a clock and you use Newton's laws to predict what happens everywhere else in the atmosphere and everything. If that works out, then your laws are good to go. That's the best you can do. Okay, so you let this go, it's going to bounce back and forth, and every time it bounces, that gives you a unit of time. Let's say we have a clock. So having a clock, having like rulers, we can measure position. So with that we can measure acceleration. But how can we measure mass? In order to measure mass, we need to know what the force is. And so if I give you a particle, let's use different color. If I give you this particle, and it's like moving in this trajectory, you can calculate the acceleration, but you don't know what its mass is. All you can tell about a particle, other than, like we said last time, like its color or its smell or things like that, you can just tell its position. You can tell how easy it is to change its position. That's how you know if it's heavy or not. You push on it, right? So all you have is this trajectory, and at every point of the trajectory, you know that when this particle is here, the clock position was here, so you know a time. This is basically your unit of time, the time it takes to go and come back. So you have your position as a function of time, so you can use that to get the acceleration. But you have no information about the mass, so how are you going to get that? Okay, you might say, well, here's an equation. All you have to do is divide out the mass on both sides. So, divide out the acceleration on both sides. Not cancel. So if you divide out that out, then you can say that the mass is the force over the acceleration. But you don't know what the force is either. You can't measure that either. So how do you measure mass? Well, this is where Newton's third law comes in. It's actually something that you can use to define or know whether something is heavier or not. Which one is heavier, which one is lighter, and what is the ratio between their masses. So Newton's third law says, let me put here, every force, every action has a reaction. Okay, that's in words. But basically the picture is like this. This particle acts on that one with a force F in this direction. That particle will act on this one reciprocally with the same force. Okay, so here's another assumption that you can use to get at when is something heavy and when is something not. So this law could be thought of as a definition of what a mass is. Okay, so now let me show you how we can use this to define the mass. So you're saying that F is equal to m1 a1, right? This particle has like mass 1 that we don't know. It has a force here. So the force is equal to m1 times its acceleration, and we can measure acceleration. This one has m2, which we don't know. It has the same force, so this part is equal to that part, m2 a2. So now, given that those two are different, we can divide out the mass on both sides. So I can say m1, I can divide out this by m1, by m2, a1, and here m2, a1, right? So this cancels that, you get m1 over m2, and this cancels that, is equal to a2 over a1. So I can measure this part, and now I can measure the ratio between the masses. And that's basically all you can do. All you can say is, I have a kilogram. I just define like a ball of mass, and I call that a kilogram. And you put that somewhere in a museum in Paris, and then every other mass is measured relative to that, right? And one way that you can measure the relative mass proportion is by looking at the relative acceleration. So if one mass is very, very high, then its acceleration is very, very low when they're interacting like that, right? So this is where your intuition comes in. So now you can answer this question once you know this. The question is, why is it when you hit a truck, you fly off and the truck just is unaffected? The reason is, of course, the truck has a very high mass, even though you applied the same force to the truck that the truck applied to you. That same force makes you fly, but doesn't affect the truck. And the reason is that law. Okay? And so if you wanted actually to measure the mass of the truck relative to you, you can do that experiment. You can just hit a truck and see the ratio of the mass, the ratio of the accelerations, and that will give you the ratio of the masses. Okay? Another way to have the same force acting on two things is, for example, have like a spring, right? A spring is something that you stretch and it comes back. So when you stretch it, it has a certain force. It applies a certain force upwards. Okay, so you put my M1 on it, and then I take another mass and I stretch it identically. Okay, so now you can argue this is identical to this, so the force it's applying has to be the same. Okay, so that's an assumption, and it's reasonable because they're identical. This looks the same as this, so it has to be applying the same force. So that's a reasonable argument, and if you do, that's one way to measure weight. So you have the same force F, and the ratio of the, once you let these masses go, they're going to accelerate, and you can do again the same thing. You can take the ratio of the two accelerations, and that gives you the ratio of the two masses. If this one is very light, it's gonna accelerate quickly. If this one is very heavy, it's gonna accelerate slowly, or like you won't even noticing it moving. Another cool thing, let's say, let me write this down again. So these ratios are inversely proportional, so it's the other way. If 2 is here, then the 2 is here. That means very, very high mass corresponds to very, very low acceleration. A1 here. Okay, so one other thing, it seems here that there's a proportionality. Another way to get more intuition into what mass is, it's basically the amount of stuff that is present in the material. So to see that, you can ask, well, what happens if I add another m? So the total mass here, you would say, well, there is the same amount of stuff here and the same amount of stuff here, so the total mass is just twice. Right? If you multiply this by 2, if you just add another mass, what should happen is that the acceleration drops by a factor of 1/2. So if you add the same exact thing to the scale and you measure acceleration, and the acceleration is exactly half what it was, then you know, okay, so mass is this parameter is just basically the amount of stuff. And then you can sort of start to verify this law. You can say, oh, well, when I have twice the amount of things with the same force, right? Twice the amount of things with the same force, the acceleration dropped by 1/2. So you can confirm that law by just sticking things together like that. One last thing, just like I said last time, this law by itself is not enough to define things. You need to know more about the structure of the force. What I've done in this video, I showed you, I don't know exactly what the force is here, but I know it's equal to the force here. And so that allows me to measure the mass relative to this one. But in real life, in order to be able to predict the motion of the planets or the atmosphere or the clouds, you need to know exactly what the force is. And the way you do that, again, you start with like with the mass. Now you can measure it relative to that. You can measure time, you can measure space, and then you can start to verify any proposed law. So I can propose, or Newton did propose, that the mass from gravity, if you have m1, this is like the sun, let's say ms, this is the sun, and then you have m earth, it's obviously not to proportion. The force between them is the sun has a force on the earth that's directed towards the sun, and the sun also has a force on it that's directed towards the earth. And the magnitude of that force is Newton's constant, some number, times the first mass times the second mass over the distance between them squared. So this is the distance from the earth to the sun. I think it's like 150 million kilometers or something like that. So here's a specific law. We know like m1, m2, we can sort of deduce them. We can measure the distance, and by, like, if you have two standard masses, like you get 2 of those kilograms, you can sort of measure the forces between them, the gravitational force between them in a clever way. And so once you measure that, and you know the distance between them, you can get this constant. And also by measuring the acceleration of those two relative to some fixed point like that, you can calculate the relative in exactly the same way here, because this force is the same. You can calculate the relative mass of the sun compared to the earth. Okay, so once you have a law like that, you can proceed to calculate and measure things and make predictions. Okay, so I hope you got something out of this video. If you did, let me know. If you didn't, also let me know. And see you next time.